Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome back to the nanoHUB-U course, Thermal Energy at the Nanoscale. I'm Tim Fisher from Purdue. And this is the wrap-up lecture for week 3. And I would just say about week 3 is what we tried to do was to derive some basic thermal properties, and preeminent among them is the specific heat. And we had to do that for different kinds of carriers. And within carriers, for example, within the phonons, we had some different models that we used. And then by the end of the week, through the help of kinetic theory, we actually used the specific heat in the definition of thermal conductivity, which is sort of the superstar property for thermal transport, right? That's the one everybody wants to know usually. And that's what we've done in this week. And we've made a lot of progress, I hope, looking at that specific heat definition. And we went through this a number of different times and showed this particular slide throughout. It's very important from a definition standpoint. And what we need to do to calculate specific heat is to take a product of the energy state and the temperature derivative of the distribution function, and we need to integrate that over k-space. That's essentially what happens. And as you probably realize by now, the k-space integrals are a little bit cumbersome typically. So for phonons, we often we convert the k-space integral to frequency space, and for electrons, we convert it to energy space. And of course, those two things are very closely connected through Planck's constant. The first big approximation we made in order to obtain a tractable solution for specific heat, at least for the acoustic phonons, was the Debye approximation. And so the Debye approximation is very, very common, especially for acoustic phonons and sometimes also for optical phonons. Those are the ones at the high frequencies here. But we have to restrict it somehow. We can't just keep integrating the linear dispersion to k equals infinity, because we won't be converging. I mean, the distribution function would potentially, but we have to limit that frequency. And the way to do it, the way that we limit the frequency, is by making sure that we're including just the right number of states, of allowable k states that are possible in the material, and no more, no less. And so by doing that, we define a Debye cutoff wave vector. And then when we translate that to the frequency axis, that gives us the Debye frequency. And again, what we're showing here are two different linear approximations, and those would be, for example, for different polarizations, like a longitudinal polarization or a transverse polarization. The longitudinal waves are usually faster, meaning that they have a higher slope than the transverse modes. Now, as I said before, the Debye model can be used for the optical branches as well, but a typically better approximation is something called the Einstein model, and that's where we take these top curves that have finite frequencies even at k equals 0. That's the infinite wavelength condition. And we say that a decent approximation, at least, is that red curve is flat, and we'll just pick a representative frequency. We'll call it the Einstein frequency. And we can convert that, of course, to an Einstein temperature through the use of Boltzmann's constant and Planck's constant. So we make that approximation. Then we go through that k-space integration. But in this case, if you'll recall, for optical phonons, it actually turned out that the summation form was the easiest. And so we used that to do the derivation for the Einstein model's specific heat. In both cases, and this is quite notable, and it's essentially because in both cases, the Einstein model and the Debye model, we are counting the allowable states properly, or we're being rigorous about counting the number of allowable states. And so in the high temperature limit, both the Debye model and the Einstein model converge to the same limit. That is a constant specific heat. And that's shown in this graph. We're comparing the Debye and Einstein models. And for very low temperatures, the Debye model in 3 dimensions gives a T cubed dependence for specific heat. And if you wanted to look for that experimentally, we said that you'd have to be at about a 10th or so of the Debye temperature. This is a normalized temperature on the x-axis. So at about a tenth of the Debye temperature and below, that's where you'll see the cubic dependency. And then it starts to turn around and it has a somewhat linear regime, and then that asymptotes, it kind of turns over to an asymptote and ultimately reaches a constant value for very high temperatures. The Einstein model also has the same asymptote, but as we get to lower temperatures, actually what's happening is we freeze out these high energy phonons, and so for very, very low temperatures, the Einstein model gives essentially a zero specific heat, which is pretty accurate for optical phonons. For very low temperatures, they're just, the occupation number is so low that they don't really participate in thermal energy storage. We also looked at specific heat in lower dimensions, and that T cubed dependence for the Debye approximation was important. The cubic part comes from the dimensionality of the problem. And so for at least for these low temperature cases, we can look at the polynomial exponent of the Debye model in 1, 2, and 3 dimensions, and that exponent is the same as the dimensionality. So we see a linear behavior for one-dimensional systems like our atomic chain, and we see a quadratic for 2D, and we see a cubic for 3D. So that's one way. If you had a material, you weren't sure kind of what the dimensionality you should use if you were modeling it, and you had some data, some low temperature specific heat data, that would tell you what the effective dimensionality of the material is, at least if it was a phonon dominated specific heat. We then moved on to the electron specific heat. We made an approximation in one of the integrals, and so we changed one of the lower bounds. We also did a small little trick. We pulled the density of states out of the integral and just evaluated it at the Fermi energy, or the chemical potential. Those are equivalent for our purposes in this course. And we found that the specific heat was proportional to temperature. That's to the power 1, so a linear proportionality. And we could express this in a number of different ways. Here we take in the middle equations here, we've substituted a three-dimensional density of states. And again, that density of states is evaluated at a particular energy, that energy being the Fermi energy. We could also express it in terms of eta sub E, that's the electron density, and so that's shown in the last equality. And then finally, we have, when we combine these, the electronic specific heat with phonons, because in something like metals, actually both carriers can absorb and store energy. We see that we have a linear plus a cubic term at low temperatures, and now here temperature is defined relative to the Debye temperature, and then a constant for high temperatures in general. So once we had the specific heat derived, we kind of took a step back and said, well, let's think about the carriers generically as particles. And we assumed this local thermodynamic equilibrium where we had a field of internal energy or internal energy density. That means a field meaning that it changes in this case in a particular direction. So we took the derivative of that internal energy field with respect to z. We used the chain rule to express it not as a derivative in space, but rather a temperature derivative. And then finally, with a little bit of algebra and some integration, we expressed the average heat flux in the z direction in terms of a grouping of factors: the specific heat, the carrier velocity, and the mean free path. That's the capital lambda here. And that product multiplied by 1/3, which comes from some geometric considerations, and that's a three-dimensional geometric consideration, that product actually is the thermal conductivity. Again, that's the thermal conductivity is the star attraction often when we're looking at solving heat transfer problems or modeling a heat transfer problem. And now this is a way that we actually took a property that we had derived for different carriers, that's the specific heat, and we use it intimately in the definition of thermal conductivity. So that's why we did these derivations in the order that we did. And this thermal conductivity it's the kinetic approximation for thermal conductivity. This slide has a few caveats about using it. It's a universal approximation, so it's certainly not a universal law. And I want to be careful not to give you the false impression that we've somehow derived something that applies to everything, because inside of the thermal conductivity and the different terms within, actually the carrier velocity can change as a function of energy or frequency or wavelength, and that can affect the way that we just handled the integrations that we did and the averaging that we did. So we were pretty loose about this derivation and just kind of trying to get the basic form. The carrier, the mean free path, lambda, also can depend on energy and direction and temperature. And so we'll have to do some things with that also and really study that a lot harder. That's actually going to be the topic for the last week of the course. So that's really what we did this week. And, I hope you enjoyed it. I think we got a lot done this week. We'll see you next week. Thanks. Bye.